Hello, astronomy meteorology students. It's Mr. Johnson here, continuing our class notes over characteristics or properties of the atmosphere. I'll remind you, taking notes is a great idea. Go ahead and pause the video if you need to get that arranged. So today we're going to be talking about temperature. To start off with, to connect to something that we've been learning, the layers of the atmosphere are characterized by different changes in temperature. You can see it pretty clearly on this graph here. We have a decrease in temperature from the surface of the Earth all the way up to where it starts to increase. Well, that decreasing area is called the troposphere. The area above it where we see an increase in temperature, we call that the stratosphere. And the reason the temperature is increasing is because that ozone layer is absorbing UV light and heating up because of it. As we continue to rise in elevation, we see another drop in temperature. We call that zone where it drops, we call it the mesosphere. And that's actually where we have the coldest temperature in our atmosphere. Above that, we see another rise in temperature with altitude, and that is the thermosphere. So what is temperature? What are we talking about? Well, when we're talking about temperature, we're measuring the moving of molecules. The faster those particles or molecules move, the warmer they are. The colder they are, meaning that just means that the particles are moving slower. And some molecules, they can change phases when this happens. So, for example, water is a really easy one to think about. If you have water with a lot of energy, it's moving around really fast. So all of those water molecules are bumping into each other and spreading out in all directions, filling whatever container they're in. That's called a gas. If you take those water molecules and you cool down the air that they're in, they will cool down too. In other words, if you lower the energy of those molecules, they will move slower. And by removing that energy, they'll move slower and they'll stick together a little bit more, but they'll still be able to move and they'll slide past each other, and that is going to be a liquid. As you cool down that water even more, as you take more and more energy away from that water, what happens is that water will tend to stick together and become solid at some point because the energy is so low that the molecules are moving so slow that they can't move away from each other. So that's a solid. We measure the movement of molecules using various units like Kelvin, Celsius, Fahrenheit. You're going to see Celsius and Fahrenheit fairly often. Obviously, we are probably most familiar with Fahrenheit. So the reason we care about temperature right now is because it affects things in our atmosphere, and because temperature oftentimes, is transferred. And there's just all sorts of reasons why temperature is important, I guess. When it comes to energy in the atmosphere, the energy can transfer; it can move. So it tends to move. Temperature moves from where there is a lot of movement. It's kind of a weird way of saying it, but there's energy will transfer from high to low. So the three ways that can happen would be radiation, conduction, and convection. And we will see that all three of those will affect our weather patterns around us. So again, the key here when we're talking about temperature is that we're measuring energy. That energy that we're measuring can transfer from where there's a high amount of the energy to where there's a low amount of the energy. It's going to happen. So we'll talk a little bit about radiation first. This slide you don't have to take very many notes on. I'll just remind you of a few things. When we're talking about energy, the majority of it on Earth comes from what's called solar energy. So that's coming from the sun. We call it electromagnetic radiation, and it can travel through all sorts of mediums, empty space, that kind of stuff. And we see the visible light portion, but there's a whole bunch of other different parts of light that we can't see. Ultraviolet rays, X-rays, radio waves, all sorts of things. Radiation can travel very quickly, and ultimately, what I want you to get away from this slide is that we have the majority of our energy, the vast majority comes from the sun. If we talk about 100% of the solar radiation, the surface of the Earth absorbs a lot of it. Some can be reflected by the atmosphere, by clouds, and by the Earth. Some of that solar radiation can bounce off and go back into space, essentially. But a lot of it is absorbed by the Earth's surface, and some of it is absorbed by things like our own atmosphere. All right. So there it is again. This is the information that if you're going to take notes over solar energy, this is the slide to do it. And again, don't take very many. Don't bog yourself down with that. The key here that I want to show you is that the energy from the sun is absorbed by the Earth's surface. It's absorbed by some of the atmosphere, and a small portion is reflected back by the atmosphere, clouds, and reflective surfaces of the Earth like snow-covered areas. Now, it's that absorption that we care about, because when the Earth absorbs the energy, it tends to heat up. Or when the atmosphere absorbs energy, it heats up. And that's where we start to get some changes that can occur. One of the ways that energy can be transferred is conduction. Conduction is movement between objects that are in direct contact. It happens best in solids and liquids. A good example of this is if we're boiling water. Well, you have a metal pan, or a metal pot rather, and that metal pot, when you apply heat to it, that heat will move through the metal. If you go to grab the handle could be warm. That handle's not warm because it came in direct contact with the heat, but instead that heat has transferred through the metal object. It is conducted through that metal and into that handle. Same thing, that heat can conduct through the metal into the liquid. So conduction is movement through a material. The atmosphere, it can have energy transfer through conduction, but it doesn't do a very good job of it. It's made of gas. An example where it can happen is if you have a really warm surface of the Earth. What can happen is that surface of the Earth can conduct its energy, a high amount of energy, to the lower atmosphere. So conduction can happen. The atmosphere, it has mass. The Earth has mass. So if there's a lot of energy in the Earth, because it was heated up from the sun, that heat can transfer to the air through conduction. It can actually physically warm the air that's close to the surface of the Earth. What that can do is that can then actually cause what's called convection. So convection is a different process where it's movement of a fluid. It's transfer of energy because of the movement, either of a gas or a liquid. So in our atmosphere, most of the energy transfer is through convection, that movement. So here's how it happens. As we just mentioned, we can have heat, warmer air that's close to the surface of the Earth. And it was warmed again by that other method we just talked about. So we have warm air. What happens is if you have air that's warm, it will spread out more and become light. And so it is less dense and it rises. As the gases cool, they tend to sink because they are more dense. So what ends up happening is we have a warmth, we have warming becoming less dense and rising. And when it gets far enough up into the atmosphere, it loses that heat to air around it. And it's cool, becomes more dense, and sinks. And so we actually have this sort of like mixing of the air. Now, this can happen in all sorts of other places too. You see this when you boil water. That water that's near the heat source, it becomes very, very warm. So it's a lot less dense and it rises to the surface in the form of a bubble sometimes. And then the relatively cooler water will sink back down toward that heat source. So next time you boil water, go and look at the water before it boils. You'll actually see that there's movement, there's mixing. Warm water is rising toward the surface, and the cooler surface water sinks back down toward the bottom. And it all has to do, again, with density. Warm air is more dense. Warm air and water are less dense, so they rise. Cool air is more dense, packs together tighter, so it sinks. Now, let's kind of think about this for a second. We've been talking a lot that the troposphere, as you increase in elevation, it becomes colder. But didn't I just say that warm air rises? So if hot air rises, why is it colder higher in the atmosphere? Well, it has to do with what happens to that air when it moves. So yes, we have warm air that's rising, and as it rises, what ends up happening is it finds itself in an area where there's less air pressure, so it can expand. Well, although it was originally really warm, that expanding causes it to cool down. If you've ever taken anything in a container like propane, for example, or like a spray can, and if you let that gas out really quickly, you'll decrease the temperature in that can. It'll become cold. So again, if you take and you like spray a bunch of hairspray, or if you spray spray paint and touch the can, if you spray it long enough, that can will cool down because you're decreasing pressure. Well, that explains why we can have warm air rising and actually cooling down. It's because it's expanding. Now, to take just a minute, we're going to talk about what's called temperature inversion. Normally, temperature decreases with an increase in altitude. So the higher up you go, the cooler it is. But sometimes that's not the case. Sometimes, under certain conditions, we can actually have it where it's cooler at the bottom and warmer above. So in this picture down below, you can see that normally, because of convection, we have warm air rising and we have the cool air above. Well, sometimes we can have cold air trapped below warm air, and then some interesting things can happen. So here are some causes. I'll give you what happened or what results in just a minute. If we have cooling of that land, because if the heat is able to escape really easily, then what ends up happening is we might actually have I'm running out of time here. If we have the land becoming cool, what was originally warm above will stay warm, but that cold air below will be trapped. It won't be able to move up. Another possibility is that we can have these things called air masses. An air mass is a really, really large kind of pocket of air that has similar temperature and moisture level. If we have warm air moving into and coming in contact with cold air, that warm air is going to be less dense, and so it's going to move up and over a cold air mass because it'll be more dense and be heavier. That will cause that lower layer to be cooler than the layer above it. Now, Los Angeles and China has this happen a lot. And what happens is because we don't have that mixing like we see in the left here, because we don't have that mixing, whatever sort of pollution happens down in this cooler layer stays there. This is how we can get smog that gets trapped. This is how we can get fire, smoke from forest fires get stuck kind of in this lower layer. But once that changes, once we get this area to heat up again, then we actually get the release and things go back to normal. So what can happen because of this is we can actually have fog down low, or we can have these lower level clouds. So next time you see a lot of fog kind of down low, there's probably some sort of temperature inversion. We'll talk more about fog later. Another possibility is we can have air pollution becoming worse because, again, it's not able to be released and spread out. It stays right close to us. And again, what ends up happening is that cooler pollution-filled air gets stuck under the warmer layer until we're able to return back to that normal layering of our atmosphere. I'm going to leave it here. I'll continue here a little bit later with more notes. Thanks for watching.